All right, class, this is the beginning of our acid and base unit. One of our objectives is to list the general properties that characterize acidic and basic solutions and identify the ions responsible for these properties. We're also going to define the terms Bronsted-Lowry acid and base and conjugate acid and base, and we'll also define an acid or base in terms of the Lewis context. I will briefly touch on Arrhenius and also the autoionization of water. Now the quest that goes with this is acid-base chemistry number 1. Let's begin. Okay, so properties of acids and bases. So let's first start with acids. Ooh, I don't like that color. Let's try that again. There you go. Let's first start with acids. We know that acids are sour in taste. Think about a lemon. A lemon is acidic, sour. We can also say that they're corrosive. So you think about battery acid from a car. That's very corrosive. We also know that they can cause certain dyes to change color. All right. When we think about common bases, we know that they are usually bitter in taste. Think soap. If you've ever tasted soap, not too fun. They're also slippery. All right. A lot of bases are used for cleaning purposes, actually, for that reason. All right. We have 3 different definitions we'll cover. We're mainly going to focus on the Bronsted-Lowry and the Lewis definitions, but the Arrhenius definition is what started it all. We've already talked about Arrhenius in kinetics, same guy. An acid, from his perspective, is a substance that, when dissolved in water, increases the concentration of hydrogen ions. So when we're talking hydrogen ions, we're talking H+. When it comes to bases, this would be a substance that, when dissolved in water, increases concentration of hydroxide ions. All right. Now, we're going to get into the autoionization of water in a little bit, but the reason he decided to go this route in defining acids and bases that way is because when you split water up, you get H plus and OH minus. Okay. So, some more definitions. Bronsted-Lowry. This is saying that an acid is a proton donor. Now, proton donor means, in this case, H+. We use H+ interchangeably. If we think about that, if you were to break it down, we know that the atomic number of hydrogen is 1, so it has 1 proton. And when it's neutral, it has 1 electron. But when it has a positive charge, there are 0 electrons. And there are no neutrons either. So it literally is just a proton. So when you say H+, it is perfectly acceptable to use that interchangeably with proton. So an acid would be a proton donor, meaning it gives up its proton. It's a base, it's a proton acceptor, meaning it takes that proton. So usually if you see the acid going down in H+, that's a good sign, or if you see the base going up in H+, that's also a good sign. Okay. We also have Lewis. The Lewis acid definition, we treat this based off of the Lewis dot structures and covalent structures, so you may need to review some of those for this unit and the rules for making those. A Lewis acid is one that is an electron pair acceptor, and a base is considered an electron pair donor. Okay, so when it comes to Lewis acid, some things we can add in here. If we have atoms with empty valence shells, they can be Lewis acids. When we're talking about valence shell, I'm talking about valence shell orbitals. So think about like the boxes and the arrows and the S, P, D, F. Atoms with empty valence shell orbitals can be Lewis acids because they want to have those orbitals filled. We're talking Lewis bases. All right, so tell whether each of the following is a Lewis acid or base, and they want us to draw structures as proof. Okay, so I'm going to draw my structures. I actually wish I had a periodic table up for this. Do I have a periodic table up for this? Oh, magically I do. Okay, so if I look here, phosphorus is in column 5A, meaning it has 5 valence electrons, and hydrogen has 3 valence electrons. So this is our little review of Lewis structures right now. So 3 times 1, this is for hydrogen, this is for phosphorus, we get a total of 8. When we draw, we want a bond to each one before we add any extra electrons. Remember, each line takes up 2 electrons, and hydrogen is happy with just 2 electrons because it only has that s orbital. All right, I've used 6, I only have 2 left, and I have this Lewis structure here. Well, that lone pair certainly can be donated in order to make a more stable compound here. So this would be a Lewis base. All right, let's look at boron. So boron, as I said, is one of those weird ones. It's in group 3A. It has 3 valence electrons. We also have chlorine, which is 7 valence electrons. So we've got 3 for boron plus 7 times 3. So that's 21 plus 3. This is 24 total. We put boron in the center. Cl minus, Cl minus, Cl minus. So we've used 6 of our 24. We have 18 left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Cool. And that is happy. What you may notice, though, is that there's this little side here that is open and susceptible to accepting electrons. So this one is also, or not also, I should say, this one is our first Lewis acid because it's a acceptor. Okay, and let's do the next two. We've got H2S. So H2S, we know that there are 2 valence electrons for each a valence electron for each hydrogen times 2, plus 6. Sulfur is in 6A. So we've got 6 valence electrons there, total of 8. All right, I got 1, I've got 2, I've used 4, 5, 6, 7, 8. Okay. Now, this thing has actually an abundance of hydrogen here. So now this one, we're going to reason by way of look at all this extra hydrogen, I want to get rid of it. So if we think about that, that goes along kind of with our Bronsted and our Arrhenius definitions. We said Bronsted are H plus donors. Well, that certainly works here. So we know that this is also going to be a Lewis acid. Okay. And since it's going to be a Lewis acid, it would accept another set of electrons, or another pair of electrons. And then it would take on a slightly negative charge. But we'll talk about that later. We have SF4, this one. So S, again, has 6. Fluorine has 7, but times 4. So 7 times 4 is 28, plus 6, we get 34. Oh man, 34, that's a lot. Okay, so I've got fluorine, 1, 2, 3, 4. I've used 8 of my 34 electrons. I have 26 left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 1, 2, 3, 4. And I said I had 26 left. Huh, that's strange. Huh? Here's something to remind yourself with. It's been a while since we've talked about it, but look at where sulfur is on the periodic table. It is one of those things that is in the 3rd energy level. Think about what's also in the 3rd energy level. We've got the 3D. So the d orbitals actually allow us to open up to more possible structures. So we can have what's called an expanded octet. We can put the last lone pair right there on the sulfur. So it would have 4 bonding and 1 non-bonding. So since that is the case, we know that we can actually have up to 6 bonds with sulfur. We could gain another lone pair right there on the other side of the axis, which would mean this is also a Lewis acid. It is a electron pair acceptor. That's a weird one because that's the getting in the trigonal bipyramidal geometry. If you haven't reviewed geometry in a while, that's okay. That's actually the unit right after this one. That's going to be a lot of fun once we get there. All right. So for each reaction, it says identify the Lewis acid and the Lewis base. Okay. So my first things first, ammonia is almost always going to be a base. And if you think about it, we know that if we were to look at that Lewis structure, we can see here we've got that lone pair that certainly is going to be donated, and thus making it a base. Okay, so that's my base, and then my acid would be nickel here, as strange as that is, because it forms that complex. So we always have an acid mixing with the base, and it forms this complex in this kind of ligand complex ion system. Okay, here, let's identify the Lewis acid. Well, H is the Lewis acid. It wants to accept a lone pair, and water in this case is actually our base, our Lewis base. We end up having a conjugate acid situation here once it gains the proton, and this would be called our conjugate acid. I'll just call it Ca, conjugate acid. We're actually going to talk about conjugate acids in a minute too. Okay. Here we go. What did I say? Conjugate acids and bases. So an acid and a base that differ only by the presence or absence of a proton. So essentially every acid has its own conjugate base. That is basically the same formula, just sans proton, or sans H+. And same with each base has its own conjugate acid, meaning we've added that proton on. So let's do this example. It says, in the following reaction, identify the acid on the left and its conjugate base on the right. Similarly, identify the base on the left and its conjugate acid on the right. Okay, well, HBr is a big sign that this is our acid because we know it wants to give up that proton. As we said before, ammonia is going to be our base. Ammonia almost always is a base. Okay, so now we have to track the formula. All right. Well, I know that if HBr is an acid, it's going to give up its H+, and that would just leave us with a Br- ion. So Br- is my conjugate base, because now it no longer has a proton. It's basic. And NH3, that proton had to go somewhere, so if I look here, I see that my protons go up by 1, and NH4, ammonium ion, is my conjugate acid. Okay, so we can look at the same thing for B and C. Let's see, our conjugate base. All right, so if we're asked for the conjugate base, that must mean this is an acid, meaning that when we dissociate, we're going to end up with H+ and HS-. All right, so my conjugate base would be HS-. Now, in reality, when we get to the ionization of water, we know that this H+ is reacting with water, and that's going to spur this dissociation. Okay, conjugate acid of NO3-, which means nitrate is a base in this case. Well, if we are adding water to it, so adding water, we would get HNO3, and OH minus. And this would be our conjugate acid. Okay. All right. So acid and base strength. So with acid and base strength, we know that strong acids completely dissociate in water. We also know weak acids only partially dissociate in water. So I actually have a really good video that shows this animation for us. We're going to watch that now.
Okay, so we know in general that when an acid dissociates in water, we have HA. It mixes with water, and water acts as a base and accepts a proton from our acid. We get A minus and H3O plus. H3O plus would be the conjugate acid, and A minus would be the conjugate base. When it's a strong acid and base, it dissociates completely. So we get pretty much all H3O plus and all A minus. And you see the concentration of HA is really small at that point. When it's a weak acid, it doesn't dissociate as much, so we see that it donates a little bit, but the equilibrium shifts back and forth, and we end up still with mostly HA in a weak acid solution. A minus is small and H3O plus is small. Here, this is a visualization animation of a strong acid. You'll see as that gets dumped in, almost instantly all of that becomes the anion with H3O plus, and there's no acid particles floating around there. Water becomes the acid, the hydronium ion. When we're looking here, Ka is greater than 1, so products are favored. When it's a weak acid, as you see here, they dump the acid in, and it takes a little bit of time, and only a few of them become H3O plus, and they kind of exist in this equilibrium state where they're bopping back and forth. And it's still mostly HA, to be honest. So it's not all that much of a dissociation. Equilibrium's far to the left. It's less than 1.
So when we are looking at this in terms of water, we have to look at the autoionization of water. Water is amphoteric. Amphoteric means it can behave as both an acid and a base. So if we have two water molecules together, they actually can ionize each other and become H3O plus and OH minus. This leads us to writing the ion product constant, or the ion product expression. So yes, we are talking equilibrium. We know that we don't include the pure liquids, but we do include everything that's aqueous or in gaseous state. So our equilibrium is going to be H3O plus and OH minus. Now, since water can auto-ionize, we pretty much can figure out that the concentration of water is not going to change. So since the concentration of water is constant, and we know that this auto-ionization will always lead us to the same K value. So what that means is that at 25 degrees, we have a K value for water that's equal to 1.0 times 10 to the negative 14th. Now, this is going to lead into a lot of our pH calculations, and this will be the basis for all things pH. Okay. So we have an example. This example has a value different, just for the sake of solving, but it says at 60 degrees, the value of Kw is 1 times 10 to the negative 13th. That value is a little bit smaller because it's got more heat, whereas before it's 10 to the negative 14th at 25 degrees. So it says using Le Chatelier's principle, predict whether the reaction below is endothermic or exothermic. Well, it's looking at the autoionization of water. We know that we have a small k. If you think about small k's, that means that reactants are favored. So small k, which means reactants favored. And if reactants are favored, that means we need energy to get this to go. So therefore it's endothermic. Okay. Now they want us to calculate H plus and OH minus in a neutral solution. Okay. Well, that's easy. We have our 2H plus. I'm going to set this up like a rice table, but we really don't need it to that extent. So they have an H3O plus here. It's a good time to talk about how H plus and H2O, that's really sloppy, sorry, H plus and H2O, when they combine, we end up getting the hydronium ion, H3O plus. So H plus and H3O plus are essentially interchangeable in that regard, okay? So you're probably going to see that a lot, which is fine. So we know that these are pure liquids. If we were looking at a rice table, we wouldn't actually include that. But if we're looking at just our change, we know that this goes up by plus X, this goes up by plus X. Now we assume that the original concentration is 0 because it was all water to begin with. And so we're causing a shift to the right. All right, so I could say X times X, which would be X squared, equals my KW value. All right, and I would just have to do a square root of this, and the square root of 1.0 times 10 to the negative 13th would give me my concentrations of H plus, which are equal to my concentrations of OH minus. Okay, all right, so the square root of 1e to the negative 13th is 3.16 times 10 to the negative 7th. So this concentration is 3.16 times 10 to the negative 7th molar. Now if I was doing sig figs with that, it would just be 3 to the negative 7th, because they actually only gave me 1 sig fig to begin with. All right. Okay. So the ion product constant. So they want us to calculate H plus and OH minus from the information given for each and state whether the solution is neutral, acidic, or basic. Ooh. All right, so we'll do the first one together, and then the other two I'll have you do on your own. All right, so here's my deal. I know that my KW is equal to H plus times OH. And I know that KW is 1 times 10 to the negative 14th at 25 degrees. So I can say that H plus is equal to my 1 times 10 to the negative 14th divided by 1 times 10 to the negative 5th OH concentration. This is going to be OH minus. All right, let's calculate it. 1 e to the negative 14 divided by 1 e to the negative 5th. Oop, I left my e out, sorry. Second e, there you go. All right, so I get 1 times 10 to the negative 9th. All right. 1 times 10 to the negative 9th. And this is my H plus concentration. Okay. Well, this is the hard part, is figuring out if it's acidic, neutral, or basic. Well, in the next play posit, we're going to jog our memory a little bit with pH. We know that pH is equal to negative log of H plus. So that means that anything with a negative 7 or lower exponent is going to be a low pH. Anything with a negative 7 or higher is going to be a high pH. High pH would be basic. This is larger than 10 to the negative 7th. This one is basic. Okay, go ahead and try the next one on your own. 1.0 times 10 to the negative 7th molar OH minus. Okay, so we have 1 times 10 to the negative 14th divided by 1 times 10 to the negative 7th. Well, looks like they're going to be equal to each other, aren't they? Or at least fairly close, right? You could probably do this without a calculator, but I'm just going to double check because it doesn't hurt. 1 e to the negative 7th. Look at that, they're the same. Oh man, what does that mean? Well, if they're the same, this is neutral. Okay, let's do the next one, C. Okay, 1 times 10 to the negative 14th, and this is divided by 10 molar H plus. So this time we're getting our OH concentration, okay? So this one might be a little bit harder to tell. All right, 1 e to the negative 15th divided by, negative 14th divided by, what was it, 10? Yeah, divided by 10, which means OH is 1 times 10 to the negative 15th, which is really small. Now remember that these are inverses, right? If H plus is going up, OH is going down. That means if you have a small OH minus, you have a lot of H plus. If you have a lot of H plus, you're going to be more acidic. So this one was tricky. This is acidic here. Okay. The other ones, we were able to just look at the value and see if it was greater than or less than to the negative 7th because we were finding H plus, right? So we want to remind ourselves that H plus equals those numbers, okay? H plus equals 1 times 10 to the negative 14th divided by 1 times 10 to the negative 7th. Okay. So strong acids, we just watched that video. We talked about all the dissociation and the things that go on there. Some of the strong acids we really need to know, there's going to be 6 main ones, okay? 6 main ones are H with this chunk here. Notice that fluorine's left out of there. HF, hydrofluoric acid, is still very, very corrosive, but it doesn't actually dissociate that much. If HF was a strong acid, oh, we would be in so much trouble. The other ones we need to know are actually parts of polyatomic ions. So it's, we've got the nitrate ion. So we've got nitric acid, which has the nitrate ion. Is of strong acid, we have sulfuric acid. And we also have perchloric acid, ClO4. Okay, so those are the 6 we need to know. So HI, HCl, HBr. And then we need to know those other 3 up there with the polyatomics. We also have strong bases. But before I talk about that, I also wanted to just remind you that the stronger the acid, the weaker its conjugate base. So think about that too. I talked about conjugate bases earlier, but I didn't talk about that specifically. So the stronger the acid, the weaker its conjugate base, and vice versa. The stronger the base, the weaker the conjugate acid. Which makes sense, right? If we're getting rid of our proton, then we're going to be pretty weak afterwards, right? Or if we're not really getting rid of our proton, then whatever is taking it is definitely going to be a lot stronger than us. All right, strong bases. We pretty much want to be aware of anything that is going to form a hydroxide or an oxide with group 1 and group 2 from calcium down. Magnesium hydroxide and beryllium aren't strong, and that has to do with their solubility. But we're really looking at hydroxides of group 1 and group 2. So hydroxides, anything with OH minus, and then oxides. So that's what we're looking at. Interestingly, the ones that are soluble are very strong. Okay, and I think that's all for this first one. Have a good day.